All right, so throughout the entire talk today, M is going to be a closed hyperbolic three manifold, and I think multiple people have mentioned that this Mostow rigidity theorem, which says that M is determined up to isometry by its fundamental group. So the question that we're going to talk about today is, well, okay, if M is determined up to isometry by its fundamental group, then you should be able to take algebraic invariants of pi1 of M and say how they relate to like the geometry and topology of the manifold. And so we'll try to understand how does the rank sort of influence the geometry and topology of M, right? And there are lots of things that we could say about how does the algebra of pi1 of M influence the geometry, and I think I'm gonna have a pretty narrow focus today, just so that we can. I'd actually like to give you some details of something for a change. So I'll just stick to rank here. In particular, all right. So we're going to talk about the following theorem. So definition. So the injectivity radius of M is okay, I'll just say it's 1/2 the length of the shortest closed geodesic. And so I'd like to tell you to start about this theorem of White from 2000 that says that you can bound the injectivity radius of M from above by some function of the rank. Okay, so the injectivity radius of M is at most a function of the rank. Okay, and maybe I should mention that there's this paper about this, but also a few other people have written similar things, similar statements. Like Grigori had sort of alerted me to the fact that actually there's a line in Gromov's hyperbolic groups paper, for instance, that says something like this. I mean, without proof or anything, but like so maybe like you can see also Gromov, and then there's a paper of Arzantseva from like 06, I think, and also Kapovich Weidman from 03.
Yeah, 08 or 00?
That's 00. Mm-hmm. Yeah. But I think none of these people. Well, maybe they knew about Gromov, but otherwise all this was sort of independent. Okay. And so the first part of the talk is going to be, I mean, really, like the first part of the talk, what I'm talking about White's theorem, has nothing to do with hyperbolic three manifolds. Okay, I mean, everything I'm going to say works in HN. Doesn't really so much have to do with HN either. But yeah. I mean, the function f here, I think. I mean, it's not explicit in this paper. Actually, I was trying to think about this. I think maybe it turns out to be like subquadratic or something, but it's not so bad. I mean, I think she actually writes down, if I'm remembering correctly, then I think she writes down like a cubic in her work. But let me not right. And then Gromov claims without proof that it's logarithmic. So so all right, but let me go through the some of the machinery necessary to prove this theorem, and then I'll talk about how to take that machinery and amp it up to prove some other stuff. So all right, so a carrier graph in M. So it's a really it's a map X to M, where X is a graph, and I want this map to be pi1 surjective. And so throughout this talk, I mean, you can sort of work in greater generality if you want, but like throughout this talk, I'll always assume that the rank of the graph is the rank of the fundamental group. Okay, so the rank of the fundamental group of the graph is the rank of the fundamental group of M, and And I'll also, I mean, these graphs in general don't have to be embedded, but I'm always going to treat them as if they're embedded. So, right. And so for the so whenever I have a whenever I have a closed hyperbolic 3 manifold, I can always find a carrier graph. Right, and I can always then take one that's minimal length. So let's suppose that X and M is like a carrier graph that's minimal length among all carrier graphs. Right, and so this a minimal length carrier graph always exists it's just an Arzela-Ascoli argument. And so what's the sort of starting point for all of this is that minimal length carrier graphs have really nice geometry. So here's the first proposition to that effect. So this is like coming from White's paper. And right, so the statement is that X is trivalent with 2 pi over 3 angles at all the between all the edges, and has I guess 3 times rank m minus 1 edges, all of which are geodesic. Yeah, and it's a nice exercise to prove this statement. I mean, here, why what's the where's the 2 pi over 3 come from? Well, I mean, the basic point is just that if you have some angle that's like say less than 2 pi over 3, then you can do a local modification to this graph that decreases the length. Okay, so you just sort of replace it's not very efficient to have 2 edges going to that vertex here, and so you just replace it with something that looks like that, and this decreases length. Yeah, and you can derive like this whole thing from that kind of argument. Okay, like from there it's you can say that it's trivalent, and once it's trivalent, like that counting the number of edges is just an Euler characteristic thing. Oh no, sorry, this is just me trying to write a period and and failing. Yeah. No, I mean, right. I just want to say that, like, in general, if you have a map from a graph into M, like the edges could like hit each other. But I want to say it's embedded. Yeah.
Sorry for asking about something that's probably a deliberate small y, but like by Arzela-Ascoli, there exists a length minimizing map, right? But the sequence of embeddings could converge to a non-embedding.
Yeah, that's right. Yeah. So I mean, right. I mean, really, like you work with non-embeddings, but you don't in this talk. Yeah. Yeah. So, okay. So here's a nice hyperbolic geometry fact, which maybe I'll call homework. So I claim that for all epsilon greater than 0, there exists an L such that no concatenation of length at least L geodesic segments in H3 at at least epsilon angles is closed. Okay, so if you have, right, so what am I doing? I'm taking super long segments, and then I'm connecting them together with angles that are not, you're not allowed to like basically just backtrack what you did. Okay, and if you do that, then the expansiveness of hyperbolic space means that you'll never be able to close back to where you started. Okay, but it's a nice exercise. Okay, so from this we can get the first a first sort of interesting statement about the geometry of minimal length carrier graphs. So I claim that so always X is a minimal length carrier graph. So I claim that X has an edge with length less than or equal to like L, which is L of 2 pi over 3. So like the L of 2 pi over 3 for this lemma. All right, so how do we prove that? Well, so the observation that you have to make here is that So first, the fundamental group of M is not a free group. Okay, so right, so pi1 of M isn't free. So they're right. I mean, everybody probably has their favorite of this. Anybody have a favorite way? Poker duality. Yeah. Right. Okay. Yep. Yeah. Or whatever. So yeah. Right. I guess my favorite is just saying that like okay, M is a k pi 1 and then you look at H3, right? Yeah. Yeah. Right. That's what you just said. Right. So right, by Daniel. Okay, whatever. So since I'll just write the sentence and explaining it right anyway. M and a graph would then be both k pi 1s for but they're not homotopy equivalent. So okay, so what do you do with this? So I know that the fundamental group is not free. So what that means is that this map from X to M is not pi1 injective. Okay. Right. So since so pi1x to pi1m isn't injective, implying that there's some loop in the graph that maps null homotopically to M. All right, so there's a loop in X that's null homotopic in M. Okay, and so then what do? You take this loop and you lift it up to the universal cover, and we get a closed loop and we get a loop in the universal cover where that's piecewise geodesic and all the angles are 2 pi over 3. Right, so you get a piecewise geodesic loop with all angles 2 pi over 3. And that implies by the fact, or by the homework problem, that some edge is short. Yeah, so then what's the proof of White's result? Well, I'm not going to do it in full detail, but basically the proof of yeah, what's up? Right, because why? Oh yeah, it's because some other point is that like, okay, they can't be less than 2 pi over 3 because this sort of picture, and then right, and then basically you say, okay, well, if none of the angles are less than 2 pi over 3, the only configuration that works is if they're sort of all 2 pi over 3 and there are 3 of them. So yeah, so then what's the proof of White's theorem? Which I remind you is that injectivity radius is less than a function of rank. Well, what you do is you just sort of iterate this argument. Okay, so you iterate, you apply this lemma many times, sort of, and you say, okay, well, first you've got a short edge, then you have another short edge, then you have another short edge. Do that enough, then you get a short cycle. Okay. Short gets a little longer each time. Right, so producing more and more short edges. But the process terminates in less than the number of edges steps. So that was right. So not less than number of edges equals 3 of rank m-1 steps. So we're guaranteed a short cycle. Okay. This is not a complete proof, but that's the general flavor of the argument.
That short cycle is not trivial in fundamental debate.
I mean, it's yeah. I mean, I guess right. You could phrase it like that. Yeah. I mean, yeah. You could phrase it like that.
The cycle is going to be embedded in the graph, right?
Mm-hmm. Yeah. Mm-hmm. All right, so okay, so let me tell you how to ramp up this kind of argument just a little bit more. And I'm going to do this thing now where I'm going to make this assumption, just a simplifying assumption for the purposes of the talk, that that I have some lower bound on the injectivity radius of the manifold. Yeah. Let me do this, and then I'm going to sort of explain I'm going to explain something that's a little bit more general than what the actual iteration is here. And then I think, yeah. So here's the right here. Here's a sort of more general version of really what's going on in that iteration argument. And let me make this, okay, as I said, like, let me make this simplifying assumption here that the injectivity radius is bounded below by something. So that'll sort of, like, all the constants that I talk about later will depend on this epsilon. And really, you don't need to do this, but I want to in this talk, okay? So here's sort of the key trick. So let's say that y inside of x is a proper subgraph. So if we have this proper subgraph, so let's let y tilde inside of x tilde inside of H3 be the preimages, and let's look at the convex hulls of the components of y tilde. Okay, so here's the sort of picture that you should have in your mind. Like okay, I'm not gonna. Please don't sue me if my angles are not 2π/3. And I should probably, yeah, okay. That really is trivial. Whatever. So okay, maybe this is one component of y tilde, and then I take its convex hull. What's up?
We'll just pretend the horizontal edges aren't there.
These horizontal edges? Yeah. Well, okay, right, because they're triangles. Right. Okay. So yeah, I guess I wanted to I wanted to not draw something that's a tree, because like the components don't have to be trees. But whatever. This one will be whatever. So okay, so you have these different components of y tilde. And then so you can make an argument that's kind of like that fact that we did a minute ago. And before, remember, what was the salient thing for the fact? Like, we used that M is not a free group. Okay, if you use instead, so it's also true that M is not a free product. And so since M isn't a free product, so you can use a sort of similar argument to say that there exists an edge in like E that's outside Y, such that well, so I can't say that the length of E is bounded in the same way that I did before, but I can say that the length of E relative to Y is bounded. So what do I mean by this? So length of E relative to Y is the length of the part of E tilde, so this is a lift of E to the universal cover, that lies outside the convex hulls of any adjacent components of y tilde. So here's the picture of this. So here I have you want to imagine this is like, here's your E tilde, and then the length that I'm talking about is like this length. Okay, so this is length y of E.
You say y is a subgraph of x,
Mhm.
proper subgraph. Doesn't that mean there's an edge that's not in x? And you were later saying that you're using it for free product.
No. I'm not done with the sentence. Yeah, right. Yeah, I'm not done with here's the whole sentence. The whole sentence is that this is less than or equal to some L, which I guess the way I'm phrasing it here, L depends on the injectivity radius. So the whole sentence is, since M is in a free product, there's an edge outside of this Y that has bounded length relative to Y. Okay, so I'm saying that I can always find an E where this quantity is bounded. Does that make sense?
Only on epsilon, or like on something about the characteristic of what you constructed?
Yeah, this is just epsilon. Okay, does that make sense? So if you're thinking then about right, if you're thinking about the iteration here, like what are you doing when you're iterating now? So at each point you're saying, okay, I have a current collection of short edges, and then I set my Y to be that collection of short edges, that subgraph of short edges, and then I find another edge that has relative length, that bounded relative length relative to those short edges. But that will also be short, and then you sort of keep going. So really, it's like you're applying this statement to iteratively rather than like the previous fact iteratively.
This is about the length of the edge outside the intervals. What about the part inside?
Yeah, I mean, the point is somehow if you're doing this argument, then right. So the point is that you're only doing this argument when you haven't already found a cycle. And so at every point in this argument, all the graphs that you're looking at are just trees. And so the convex holes the convex holes really look like they're like bounded blobs inside of H3. And so like there's the difference between relative length and length is bounded. Okay, but the real thing I wanted to get out of this thing is the following proposition, which I'll keep up here for later use. You can find this, this is like written in, this version of it is written in this paper of mine from 2009, which says that, right, so if x and m is minimal length, then there exists, a chain of subgraphs. So I start out with the empty set, and then that's contained in y1, which is contained in more graphs all the way up to ym equals x, such that for all I, for each edge E in yi plus 1, the relative length of E relative to yi is bounded. Does that make sense? So and how do you construct this kind of thing? Well, you just sort of like apply this observation over and over and over. Okay, like I have. What's up? Yeah. In the way I'm stating it here, then m is epsilon thick, but again, like none of this is really necessary. For the first part of the talk, I'd really just like ignore all the epsilons. Like they're not. I just want to put them on the board so that I don't say wrong things. Any questions about that statement? Yeah, what's up?
So is E in yi plus 1 minus yi? Or?
I mean, it's. I could write that, and the lemma would have the same content. The point is that if you have an edge that's in yi, then its relative length is 0, because it's like entirely contained in this convex hull. So, but yeah, this is the content of the lemma. Yeah. Any more questions on that? Maybe let me just, as a disclaimer, let me say that. So in the future, I'm going to stop looking at the universal cover in sort of an abuse of picture, and start thinking about relative length sort of more as like in the manifold. So like you're sort of supposed to imagine now like, okay, maybe here's like one component of yi, and then you have some other component of yi somewhere else. So y1, y2, and then these are like the convex holes. And okay, so then you have the rest of the manifold somehow. And when I'm going to think of relative length, I just want you to think of that length.
So the yi's are not necessarily connected, right?
The yi's are not necessarily connected, yeah.
Two different pre-images.
Right. And so these things that I'm drawing here is convex holes. They're really like the projections of convex holes from the universal cover. They don't really have to be embedded or anything, but that's the general picture. Other questions? Yeah. You mean like a
Just a little bit confused about the logic of it, because the white theorem is giving an upper bound of index idea.
yeah.
Fixing things.
Is it the same help?
What?
You need help.
No, it's like this. It's the same L. It's well, I mean, it's different L from the. That's true, right? Yeah. Like in the White theorem, like it's not a problem if the injectivity radius of the manifold is very small, because you're trying to bound it from above. But let me, if you want to know more about the epsilon, let's talk about it afterwards. Like I can tell you, it comes from like the guts of this kind of proof. But like right now, just pretend there are no epsilons, and you'll get 99.9% of the content of the talk. All right. So let's see what we can prove with that theorem. So let's suppose that S is a closed surface of genus G, and let's take a F to be a homeomorphism. Okay, and so I'm gonna want to say something about the mapping torus of F. But the thing I want to say about the mapping torus has to do with the curve complex of S. So let me just say what that is briefly. Well, I guess hey, there was a paragraph a minute ago, right? Okay. Wait, did you just Nathan? Did you just define the curve complex or no? Right. Okay. Right. So okay. So the curve graph of S is so C of S. So this is a graph. What are the vertices? So the vertices are essential simple closed curves on S up to homotopy, and the edges connect disjoint curves. Okay, and if I have a homeomorphism of the surface, then this homeomorphism acts on the curve graph via automorphisms. Okay, and if we metrize C of S, so edges have length 1, then we can define the translation length of F. So I'll call this tau of F. And so tau of F is just like the minimal amount that you translate a vertex. Okay, so F acts on the curve graph just by, because you can apply it to a curve. And then the translation length is this minimal displacement. And if this is unfamiliar to you, then it's really not a big deal. Just think, you're supposed to think of it as a notion of complexity for F. Okay, so right, so a very complex F you would think of as having large, well, you might think of as having large translation length. Okay, and so there's this theorem from O2 by Bachmann and Schleimer that says that if the translation length of f is at least 4G. So remember, G is the genus of this surface here. Then the mapping torus MF has a Heegaard genus 2G plus 1. Okay, so right, maybe remember from last time that like whenever you have a mapping torus of a genus G surface, then the Heegaard genus is always at most 2G plus 1. So this the point is the lower bound. Okay, so the point is G of MF being at least 2G plus 1. Okay, and so the thing I want to talk to you about now is an analog of this theorem for rank. Okay. So this is a theorem with Juan Souto. I think it's like 16 or something. Right. So what does it say? It says that there exists some some L depending on G, such that if the translation length of F is at least L,
All these things called L.
okay, how about let's call it how about upside down T? Is that better? No, that's terrible. All right. If tau of F is at least D, then the rank of MF is 2G plus 1. Okay, where again the point is the lower bound. And maybe I'll say, like, for homework, construct MFs with rank less than 2G plus 1. Okay, so if you want to get some more intuition for that, I'll leave that for later. Any questions on the setup? What's the question?
You mean this question for a minimum genus fiber on a vibration of?
Well, I mean, yeah, I guess I just mean, like, right. I mean, you fix surface, you have a mapping torus. Like, the translation length depends on that surface that you're fixing, and then if that translation length is big, then the rank has to be 2G plus 1.
So I guess my question was, are there known examples of mapping tori which that when you look at M of F and you pick the smallest genus representative for any vibration of that three manifold, still that inequality?
I think it'll be a posteriori if it's smallest. Yeah, if you pick another vibration, the translation is over. All the homework.
Yeah, I mean, I guess well, you're asking something more subtle, right? Yeah. No, I mean, I bet you can. I don't know, like, off the top of my head, but I bet you can do that. Yeah. So okay, so I think what I'd like to do is let's see. Okay, so what I want to do is I want to actually sketch for you a proof of it, like some of the proof of this, just because I think it, yeah, I mean, it's kind of a nice argument. So here's sort of how the proof goes. So very briefly, okay, so for the proof, so we can assume M is hyperbolic. I mean, the point is somehow that if you have this large, like, if you have a translation length that's like bigger than 2, then or bigger than 1, then you're hyperbolic. So and let's also assume that the injectivity radius of M is at least epsilon. Okay, it's not necessary, but let's assume that. So then it turns out that this translation length, so you can totally forget about the curve complex, because this translation length turns out to be approximately like the distance around the mapping torus, the hyperbolic distance around the mapping torus. Okay, so like the circumference MF, which is like the, I mean, if you want to state it precisely, it's like the smallest length of a loop in MF, projecting non-trivially to S1. Okay. And so how do you, so then what we have here is, so we want to say, okay, let's assume that we have this mapping torus where the rank of MF is less than or equal to 2G. But the circumference is, so the picture you should have in your mind then is like this, here's this huge mapping torus. And like the hyperbolic distance around the mapping torus is colossal. Okay. And so what do we do? Well, we want to take a minimal length carrier graph. So let's let X be a minimal length carrier graph. And let's let, we're going to pick our chain of subgraphs like from the proposition over here. And just for simplicity, let me assume in the following argument that all the yi's are connected. Okay. So for simplicity, let all yi be connected. And then somehow I'm looking for a contradiction, right? I'm assuming the rank is less than what I want, but you've got a huge circumference, and now I want to go for a contradiction. So what do we do? Well, we show inductively that no yi can encircle MF. Okay, so no yi has a loop that projects non-trivially to S1. Okay, and if I can do this, then that's a contradiction when you set I equals M. Does that make sense? Okay, because I mean, I know that the X is a carrier graph, so X does go all the way around M. Why? Or because
You're using the capital M as an index?
oh no, this is, well, okay, sorry, this is the lowercase m, but I get that it's okay. Yeah, is that better? Like, right, little m. Yeah, okay, they do look the same. And so what's the argument for this? Well, you just say, okay, so step one, this is an inductive argument, right? So step one is like, look at y1. Well, y1 has bounded length, so it doesn't encircle M. So great. What's step two? So for step two, like if we're going to try to show that y2 doesn't encircle M, I need to understand y1 better. And so what I say is that so the image of pi1 of y1 and pi1 of MF, okay, so by step one, like y1 doesn't encircle M, so the image of pi1 y1 lies in the fiber. And so maybe I'll call it like F inside of the fiber subgroup. All right, and then what can we say about this F? Well, so I claim that the index of F is infinite. Why is the index infinite? It's because the rank of pi1 of y1 is, well, it's less than the rank of pi1 of x, which is the rank of pi1 of, or which is at most 2g. Okay, and if you take a finite index subgroup of a surface group, the rank goes up. Okay, finite index subgroup of a certain surface group, the rank goes up. This has rank less than the rank of the surface group, so that means it's got to be infinite index. And so that means that F is free, because it's an infinite index subgroup of a surface group. And so what you get from that is, well, okay, what three manifolds have free fundamental group? So handle bodies have free fundamental group. And so you get from that actually that the convex hull of this yi is a handle body with whose pi1 is generated by this bounded length graph y sorry, I started writing yi, didn't I? This is a 1. CH of y1 is a handle body whose pi1 is generated by this bounded length graph y1. Okay, and so let me draw you a picture of that. So here's what your handle body looks like, and then there's this bounded length graph inside of it, and right. So if I'm looking at this convex hull, then okay, maybe this. If you're familiar with this, then this will be familiar. But if not, then believe it. So the boundary of the convex hull here is an intrinsically hyperbolic surface with injectivity radius bounded below because of our assumption, well, in the way I'm presenting it, because of our assumption on injectivity radius. And so it has bounded diameter. And so here's the picture. Like even if this part of the argument was a little hard to follow, the picture should be easier to follow. I have this convex hull. Its boundary is like bounded in diameter. And so where do I draw this convex hull in this picture? I mean, it's somewhere. Okay, maybe this is my CH of y1. But it's contained in this like bounded chunk of the mapping torus. And so then what do I say? Well, now I say that that all the edges in y2 are bounded outside of that convex hull. Right, so all edges of y2 are bounded outside of this convex hull. So y2, that means they all look like this or something. Or this is again bounded. So y2 only extends a bounded amount further along the mapping torus. What?
Chain.
Well, the size of the chain is most the number of edges, which is like 3 times rank minus 1. All right, and so then right. So as Uri is saying, like keep going. This terminates in at most 3 times rank m minus 1 steps. And so if you only extend a bounded amount each time, there's no way you can get around the whole mapping torus. Yeah, I mean, you need to, you need like a covering theorem on that. This is like a theorem, like if you have a pseudo-Nosov monogram, then it's hyperbolic. Yeah, I sort of elided that, but yeah. That makes sense. Yeah, all those. Maybe come up and ask me. After that. I think that's 30-second answer. Yeah. But I'm happy to talk about it. Yeah. Well, okay. I mean, I want to give exactly something many course. So that's that. But maybe I'll just end by just stating quickly. I just have like 2 more minutes or like 9 minutes. So by stating quickly a couple of the results on the rank. So there's something more recent theorem. I guess it came out in 18, although right. I mean, we just did revisions on it like earlier this year. It's a long paper. So what this theorem says? So the theorem says this is sort of like the ultimate version of all these techniques that we've been able to do so far. And what it says is that if so let's suppose that that we have this closed hyperbolic 3 manifold, and I tell you that its rank is at most k, and its injectivity radius is at least epsilon. And here the injectivity radius assumption is actually necessary. It's not just something I'm doing for this talk. Then, right. So then, sort of just briefly, M decomposes as follows. So I'm just going to draw you a picture of what M looks like. And here's the picture. Whatever. So what's the content of this picture? So the content here is that you can actually sort of decompose your manifold in a way that it looks like a graph whose complexity is bounded by the rank. So here so these pieces here are compact submanifolds with bounded diameter. Okay, and so notice that all the constants I'm telling you about here depend on the constants that I've picked up there. That's sort of the content of the statement. And these things are what we call like long product regions, where a long product region it's homeomorphic to a surface times an interval, in a way where the geometry is sort of bounded in the fiber direction. Okay, and also the sort of complexity of this picture, like the number of pieces, is bounded in terms of the rank. And so from this you can get a lot of cool results, and maybe I'll just end by stating one thing, since we were talking so much about Heegaard genus earlier. So one thing that you get from this is that the Heegaard genus of M is bounded above by some function of, well, not just the rank, but the injectivity radius. So you remember I stated earlier, like it's unknown whether Heegaard genus is bounded above by a function of the rank, and that's still unknown, but we know it's bounded above by a function of those two invariants. All right, that's all.
Questions for Ian?
Yeah, what's up?
I'm pretty mentioned this. Can you say again where the factor is 3?
Yeah, it's just like this is like the number of edges in the carrier graph, and it's just like an Euler characteristic thing. Like that it's trivalent. Yeah, right. The 3 is, I guess, coming from trivalence, and then you.
Along these, because long product is you find them in terms of like
I mean, are you asking sort of if there's like like this model manifold decomposition of them, or not something different? Yeah, well, yeah. I mean, you should sort of imagine. You should imagine, for instance, that if you take like a bounded length curve on this boundary component here, and a bounded length curve on this boundary component, then their distance in the curve graph is sort of like the length of this product region, in some sense. Yeah, only because like I only know about genus 2 surfaces. No, like no, you don't. Yeah. So the only thing you can say about these, I mean, the genera of all these surfaces are bounded in terms of K. But yeah, I mean, but they might vary. And the graph, I mean, this is like a graph that's like a 2 vertices and 2 edges going between them, and the graph could be more complicated too. But the complexity of it depends only on K.
Yesterday you talked about this cover of congruence, this tower of congruence covers of arithmetic manifold.
Mm-hmm.
The injectivity radius has to get bigger and bigger and bigger, right?
Mm-hmm.
So what does like White's theorem or all the souped up versions of White's theorem say about the behavior of rank as you go up the chain?
Well, I mean, White's theorem says that I mean, White's theorem just says that it increases, I guess, right? And and I guess if you if you actually do quantify White's theorem, then you can get some sort of statement about at least how fast it increases. Like this stuff, I don't think it tells you much. I mean, like for instance here, yeah, I mean this doesn't really help you understand that too well.
But it doesn't create the fixed cost thing, right?
No.
So these carrier graphs, how many sample back? They tell you a lot about the manifold.
Yeah, I mean, I guess you have I mean, you'll have only finitely many. And
Last week, I just heard one Souto talking about counting those. I think they have some specific.
oh, really?
Yeah.
Oh, he was doing something. Yeah, I didn't know about that.
Implementation is not. Oh,
Huh. Oh, okay, cool. Yeah, I mean, there's yeah, well, okay, I haven't talked to him about that. So yeah, maybe he has some work on counting them or something. But yeah, but I mean, I don't think Yeah, aside from whatever that is, yeah, I don't really know. I mean, there are finally many of them, you know, don't really know where they are. I mean, you should sort of like, well, what does that mean? Like the same set of like, you know, graphs up to isomorphism or something? Up to isometry? I mean, probably, I would say. Yeah, probably, although, yeah, I'm sure one can do that, although I would have to actually think to come up with some examples.
Any further questions? Let's thank Ian for a great